Thank you so much. Hi everyone, my name is Wendell, and I'm going to present to you my master thesis. It's remote sensing the key water quality indicators in Manila Bay of the Ville from Laboratoire d'Oceanography of Villefranche-sur-Mer in France. So approximately 40% of the human population inhabit along the coast, and they are socio-ecologically important, but they've been facing human pressures, for example, resulting to harmful algal blooms, and that it is important to monitor the water quality in these ecosystems. Traditionally, the water quality samples have been assessed using field sampling, but the recent techniques lead to capturing images of the ocean. The process is called the remote sensing of the ocean color. The principle is that the ocean color works with light. The ocean color studies focus more on the visible light, the near infrared region, and surely the near and the sphere. The sun is the source of light, and the light travels to the earth, and it is known as the downwelling irradiance. There will be light that will be reflected by the atmosphere, and there will also be light that will be reflected by the sea surface. And most importantly, what we need here is the water leaving radiance. However, in order to radiance, we need to correct the atmosphere first by removing the influence with the reflectance. And secondly, we need to mask the clouds and to differentiate clouds between the ocean. In another aspect, we have the remote sensing reflectance. It is basically the basis of the satellite data. And by formula, it is the ratio of your water leaving radiance to the downwelling radiance. It is important that wavelength interacts differently and is dependent on the nature of the particles. So for example, here in this photo, we see the reflectance graphs. And we can see that in different regions, there's a difference in the graphs, and therefore noting the difference in the water quality. Hence, we can estimate chlorophyll A, which is basically the proxy of water's productivity, and the SPM, which affects the light penetration using the RRS. So there are many algorithms about the common ones. For example, the chlorophyll algorithms, we have the OCX, and simply it estimates by the ratio of the blue and the green wavelengths. They improved with another algorithm. It's called the GSM, and it also accounts non-algal particles. For SPM, it can be estimated using wavelength at 645 nanometers. There are many existing at this moment, but we want to explore the potential of MODIS from NASA in Manila Bay. So it has high temporal resolution of also have a spatial resolution of up to 250 meters. And there have been many attempts in Manila Bay in using the satellite data for chlorophyll A and SPM specifically. So for example, the Philippines microsatellite, which was launched in 2016, it was of water pollution. And in another study, they tracked the extent of sediment transport in the northern part of the bay. And more importantly, there's only one study that uses the MODIS satellite using the monthly composite with a spatial resolution of 4 kilometers. And if you can see from the image there, it has a low resolution of the image. Lastly, there has been no attempt to reprocess the MODIS data to accurately estimate the chlorophyll A and the SPM of the area. The study is to reconstruct the MODIS satellite daily images into higher resolution with appropriate processing parameters. And after this one, we want to answer the following questions. Are the MODIS images potentially reliable data for studying Manila Bay's chlorophyll A and SPM dynamics? And the second one would be, will it be able to capture spatial and Manila Bay? So in order to do the following objectives, we did such methodologies. So first, we have selected Manila Bay as the study area for one reason, that it is a pollution hotspot in Southeast Asia, and also it's located in the capital region of the Philippines. It has 2 seasons of weather, mainly distinct with rainfall and wind monsoons, the dry and the wet season. The area is surrounded by major rivers, but only 2 of them contributes to the highest percentage of the fresh water supply. We have the Pampanga River in the north that accounts 50%, while Pasig River for the 21%. And for anthropogenic influence, we can see that in the west, in the Pasig River, there is an untreated sewage input to the Manila Bay. And also in the north are the unregulated agricultural waste. Previous studies have used chlorophyll A and SPM, especially in 2010, to assess the water quality. So in this study as well, we as the in situ basis for this present study. For the satellites data, we have the level 1A data downloaded from the NASA website, and we use CDA to derive chlorophyll A and SPM and also the processing parameters. In a nutshell, the whole processing resulted into something like this. So for example, we have the image of February 11, 2010. And when we use the NASA's website default chlorophyll A data, it has a default level 2 with 1 kilometer resolution. And it uses the default processing parameters. This present study, however, we move back one step behind, and then we reprocess the level 1 data instead to produce level 2 images. And then we have the 250-meter resolution, and then we modify the atmospheric correction and also the cloud masking. How does the data processing work? So basically, we have level 2 daily images. And then, for example, in the month of March, these are daily images, and you can pool them statistically to produce. So to be more specific, the following workflow was followed. But in this presentation, we will not be discussing in details about the theories, but we will only run through about the process. So basically, we have the atmospheric correction. We selected between 2 algorithms to see which one is appropriate in the area. And then also we masked the clouds with 3 different processing schemes. We have the default and the 10 times cloud threshold, and then we use the other one with the sphere. And then next, we selected the algorithm appropriate for the area, most specifically for the chlorophyll A. We compared OCX and the GSM algorithm. But however, for SPM, we only use one algorithm that have been used in many studies before. So after that, we have the satellite validation, and we follow the protocols of removing the outliers and getting the accuracy with statistical parameters such as bias and regression slopes and etc. So after that, we made a composite map specifically for the monthly median of the daily images. So after these methods, we come up with the following results. So during the year 2010, there were only 318 satellite overpasses in the Manila Bay area, but about 78 only of them were usable and considered cloud-free. So in the graph shown in here, basically this is the distribution of the satellite images that was available during the month, per month, and then we observed that there is a skewed pattern of the cloud-free images in the area. So we can see wet season really has a low number compared to the dry season, and we had the highest coverage during the month of February. In selecting the appropriate atmospheric correction, for example, here we use again February 11, 2010 as an example with the NASA's default setting for the illustration in here. So here we have a true color MODIS image. When we reprocess the image with the near sphere atmospheric correction, we can see here that it failed to retrieve chlorophyll A smoothly. But when we use the MOM atmospheric correction, we can compare that there was a smooth retrieval of the chlorophyll A. So it means that MOM atmospheric correction basically performed better than the other one. We also did the same thing, and we obtained the same conclusion for the SPM results. For the cloud masking parameters, here we have 3 different schemes. Using the same example date, and then we have a true color MODIS image here for the February 11, 2010. So for example, in the red box in here that I highlighted, it's a sample cloud that we wanted to mask. So in the first processing, the setting failed to retrieve the clouds. However, when we increased the cloud threshold to 10 times, we were able to obtain the water chlorophyll A, and then the clouds were also masked successfully. Obtain a more accurate masking of the clouds when we use the sphere wavelength. We can see here that the cloud edges were perfectly differentiated from that of the water, and then therefore reducing the contaminations of the samples. So we use sphere cloud masking instead. For the chlorophyll A algorithm, we found that GSM has higher accuracy in estimating chlorophyll A. So if we see the validation in here of the table, GSM has 2 times less RMSE, or the root mean square error. It also has less mean absolute percentage error. And also we obtain a higher correlation and a higher slope in GSM as compared to the OCX. In general, the OCX failed to estimate the higher chlorophyll A values, and then hence the GSM chlorophyll performed better in this scenario. And also, lastly, we want to highlight that we were not able to establish a relationship between SPM validation, but we still use them in this processing in the assumption that it can produce spatial and temporal variations of SPM. Now we take a look at the monthly chlorophyll A data that was generated here in the study. So we have monthly maps, and then we have an illustration here just for the sample representative for the dry season and the wet season. And let's take a moment to observe the illustration of the chlorophyll A. If we focus on the red box in here, we can see that the chlorophyll A plume generally disappeared in the dry season. And also, if we move back to the northern part, we can see that the rest of the bay, it had higher chlorophyll A concentration, and then it even extended, especially during the wet season. And lastly, the middle portion of the bay, we notice its intensification in the wet season. Especially in September and October. So in another parameter for SPM, we did the same thing, produce a time lapse for the month of for the year of 2010, and then we have representative months for dry and wet season. And let's take another moment to observe the time lapse of the year 2010. If you look at the red box in here, we can observe that the pattern of SPM plume generally fluctuate in 2010. And in another section here, we can observe an extension of the SPM plume during the wet season, and then it can even extend up to 15 kilometers from the coast. And lastly, the middle of the bay highlighted here, we can observe low SPM in general, but we can see an intensification, especially in the months of wet seasons of September and October. One of the most interesting findings that we also want to highlight is the super typhoon in October 2010. If you look at the satellite tracking of the typhoon, it entered the Philippines in 15 and then left at around 20 of October. If we try to look at the weather data and the river discharge of Pampanga River, we observe the coherence of increase of wind speed, the increase of rainfall, and river discharge during those days. The satellites were able to capture the events and changes of chlorophyll A and SPM. So for example, in October 9, we can see that the chlorophyll A high concentrations were more localized in the northern part of the bay. But during the typhoon, we observed a slight increase in the middle part of the bay. However, a week after the typhoon, we can see that there was a widespread occurrence of the high concentration. All the results that we have, we wanted to know if we were able to answer the following questions. Are MODIS images potentially reliable for studying Manila Bay's chlorophyll A and SPM dynamics? When we use NASA's default, then we can say it is not reliable because it's made for the open ocean. But however, when we reprocess the data with appropriate parameters of atmospheric correction and cloud masking, we can say that it's reliable since they are appropriate for the area of the study. In another question, we wanted to answer, will it be able to capture spatial and temporal dynamics in the Manila Bay? And yes, spatial and temporal variation showed realistic variation with respect to the weather season. And we also was able to capture the typhoon disturbance, which can be associated with high wind and high river discharge, as evidenced by high chlorophyll A, and is also supported by the previous studies that in typhoons, nutrients can be upwelled in that area. To conclude the study, we found that it may be appropriate to reprocess MODIS images in the following conditions: 250-meter resolution, the MUM atmospheric correction, the SWIR cloud flagging, and for example, for the chlorophyll A, GSM is more appropriate. And then we also concluded that it is potentially reliable in the area of study. However, SPM needs more validation. And also, we observe realistic spatial and temporal variation of chlorophyll A and SPM in accordance with weather seasons. So the authors would like to recommend a further validation and a multi-sensor validation of the satellite data. And also, especially with the Philippines microsatellite, it can be combined and give a sounder approach specific to Manila Bay. So before I end, I would like to thank these following people: David Docsaran, my supervisor, for being the most patient person; French people for the help and support during the formation of the study; and most especially to Lara Soto and Sir Gil Jacinto for being responsive and for letting me use their in situ data. Thank you so much.